Hey guys, welcome back to lesson number 3 in the Foundations of Algebra course. Let's get right to work. We've been spending a whole lot of time talking about the real numbers in our past couple of lessons, but that's because algebra is the study of the operations on the real numbers. And as you guys know well at this point, the real numbers are the integers and all the numbers in between. So we've really been diving into those numbers in between. And we started with a really important set of numbers, the fractions. Okay, fractions are numbers, and they're the guys that live in between the integers. So remember, they're just numbers like 3/5, 1/7, 97%, 4/11, etc. Today's lesson is going to extend that a little bit. We're going to talk about mixed numbers, and they're numbers of the form 2 3/5 or 7 1/4. So it's just a whole number part together with a little fractional part. 2 3/5 is just 2 plus 3/5 more. All right. So just to help get you settled, let's look at them and represent them like we did just our regular fractions in our previous lesson. 2 3/5, if we want to represent that with bars, just like we did our other fractions. 2 is no problem. We all understand 2. There's 2 bars, shade them both in, and now we need to represent the 3/5. So take a bar, 5 equal pieces, shade in 3 of them, game over. You're looking at a great representation of 2 3/5. Now, just numerically, just to get settled here, if you've got 7 2/5 miles, you've run that already. It's a long run. 7 2/5 miles. If you run one more mile, how far have you run? Well, we're just adding one more onto 7 2/5. So that just means that we're going to have 8 2/5 miles when all is said and done, right? 7 2/5 more, add one more whole mile onto that, 8 2/5 miles. What if, though, you were in this situation? You had 3 7/8 miles run, and then you run 1/8 more. How far have you run in total? Well, here, just a quick visual, because now we're playing with those the fraction parts, right? So 3 miles, no problem. There they are. We've run that far. Now 7/8, there's that. Now we're going to add 1/8 more onto this, okay? So that's just going to fill in that last 8 that we were missing, isn't it? And it actually completes that 4th mile. So you know what? We've run 4 full miles. Looking good? All right. Just like with fractions, you're going to see mixed numbers all over the place in the real world. Let's say you wanted to pour 2 3/5 gallons of pink paint, interesting, into these 1-gallon containers. All right, well, you got some containers laying around in your garage, let's say, and you want to pour. I gave you like $1,000 for special effects. This is what we get? It was like a block. Come on. It's my mom. She's in charge of special effects. She's not doing great. She's lucky I love her. There's 1 gallon of pink paint. Let's pour another full gallon. There's 2, and now we got to pour in 3/5. Well, I only need that third gallon container, right? Let me take it, divide it into 5 equal pieces, and let's pour in 1/5, 2/5, 3/5 more. It's amazing how it just stays together in the air like that. 2 3/5. There you go. Nothing to it. All right, let's go through the basic ideas, just seeing how they hit with mixed numbers, just like we did with fractions. All right. For example, close to. 2 1/13 is very close to 2. Why? Well, 1/13 is very close to 0. See how our knowledge of the fractions is really going to pay off here? So 2 plus almost 0 added onto it is just close to 2. And 2 12/13, since we know 12/13 is very close to 1 whole, that means we're really close to 3 with 2 12/13. All right? Leftovers was a big basic idea that we saw with fractions. So for example, you want to run 10 miles. You've already run 6 5/8 miles. How much is left to run? Well, you might be able to see it with the numbers. And in fact, I think you want to be able to see it with just the numbers. But here's a quick representation. There are all 10 miles represented. 1 mile is represented by 1 bar. We've run 6 and 5/8. There we go. So what's left? Now it's just a matter of reading that off. You can see we've got 3/8 left to go in that 7th mile. So if we do 3/8 more, we're at 7. And then we've got 8, 9, 10. 3 more miles to go. You can see them in the unshaded bars there. We got 3 and 3/8 miles left to run. All right. Very nice. Half was a really important benchmark with our fractions, and it stays that way in the mixed numbers. For example, 4 and 5/12. Is that less than or greater than 4.5? Well, I see you looking. I can see your eyeballs looking at the 5/12 part. That's really the crucial thing. So ask yourself, is 5/12 less than or greater than 1/2? And based on our work before, we know that that's less than a half, right? Because half is 6/12. 6/12. We've only got 5/12. So that's less than a half. So 4 and 5/12 is less than 4.5. In other words, there we go. 4 and 5/12 is definitely less than 4.5. Good. We've been talking about obvious comparisons with our fractions, and we should extend that to whole numbers as well. So let's say you want to put these numbers. Some of them are mixed numbers, some of them are whole numbers. Let's put them in order from smallest to largest. Well, in this particular case, boy, this is almost beyond obvious, isn't it? The whole number parts almost take us all the way through. So, for example, 0, that's clearly the smallest of those 5 numbers. Then, who's next? Well, all right, now the next 2 smallest numbers seem to have 3 as the whole number part. One of them is only 3. So 3 is less than 3 and some more. 3 and 9/10. Now 3 and 9/10 is very, very close to 4, right? But not 4. 4 is the next one in line, and then clearly 7 and 1/6, 7 just by itself, that whole number tells us that 7 and 1/6 is the biggest of all 5. Looking okay? Well, what if it's not so obvious? Even if they're closer, maybe we can take advantage of our obvious comparisons. Let's take a look. Look at those 5 numbers. I see 2 as the absolute smallest, and 5 and 1/2 as the absolute biggest. Does that make sense? Just looking at the whole number parts. So tell you what, I'm going to put 2 here, and I'm going to put 5 1/2 down at the far right end. Now, it just becomes an issue of looking at those 3 mixed numbers that have 2 and a fraction part. But look, we can ignore the 2 because they all have it. Let's concentrate on the fractions, and it just becomes a question of, are there obvious comparisons that we can make here? Well, look at this. 3/13 and 3/11, those are both less than a half, but 4/5 is more than a half. So 2 and 4/5 is the biggest of all 3. Put that one there. So it just, now, let me take him off the list. It now just becomes a question of, well, what's the order between 3/11 and 3/13? Well, good. Oh, I heard somebody whisper that. So quiet. Where is that? Who said that? So quiet, but exactly right. It comes down to, because we have 3 of 3/13 and 3/11, same number of pieces, it comes down to the size of the pieces. And we've seen before that the bigger the denominator, the smaller the pieces. So 13ths are smaller than 11ths. Game over. 2 and 3/13 is smaller than 2 and 3/11. Oops, sorry. Here's my last little less than symbol. There we go. We got it. Very nice job using the stuff that we've mastered from before. Good. I'll tell you what, here's a related issue. What do you think we mean by that fraction? 7/4. It's a little different than the ones we've seen so far because this time the numerator is bigger than the denominator, isn't it? Well, let's use our bars to make sense of this. All right, there's a bar. If I split it into 4 equal pieces and keep all of them, that's one whole, right? 4/4 is 1. But we need 7/4. That means we need more than one bar. So we'll go to another bar. Let's split it up into fourths. And so we already have 4 of them from the first bar. So we need 5, 6, 7. There's 7/4. Well, by looking at the bars, you can see that that's really just saying that 7/4 is the same as 1 3/4, isn't it? Good, good. Wait, here's something interesting. What if instead of 7/4 we had 8/4? Well, that would mean we would just need one more fourth, right? Let's put him on. But guys, that's just 2 bars, 2 whole bars. And I don't know about you, but I'm seeing something here. Look at that, 8, 4, and 2. Something big's happening here. Guys, 8 divided by 4 is 2. And that's showing us a really important relationship. You ready? Here's a huge fact. Fractions really correspond to division, okay? That's really important. Doing fractions is really doing division. And we can use that fact right away. Fractions correspond to division. So let's say you wanted to convert 17/5 into a mixed number. Oh, by the way, 17/5, we're just going to call that a fraction bigger than 1. Okay? Some people call it an improper fraction. That's fine, but to us, improper sort of has a negative feel to it. It's just a fraction, and it's going to end up being bigger than 1. And the tip-off is the numerator is bigger than the denominator. Okay? Let's say you want to figure out what mixed number that is, or what number that is, 17/5. Well, you just divide it. We don't want to have to draw bars every time. So 17/5 is the same as 17 divided by 5. All right, well, 5 goes into 17 3 times. Subtract it, and I get 2 left over. So it goes in 3 full times, 3 wholes, with 2 left over. 2/5 are going to be left over. 3 and 2/5. That's our mixed number. You just divide them. Good. What if we want to go the other way? Let's say we've got a mixed number and we want to convert it into a fraction. Well, that means we want to take 2 1/4 and write it as some amount of fourths, just a single fraction bigger than 1. Well, you guys understand, we just need to figure out that numerator. And it turns out that the way we get it, you might remember this, it's just 2 times 4. That's coming from right here. Okay, 2 times 4 plus 1, plus this 1 up here. All right, and 2 times 4 plus 1, 2 times 4 is 8 plus 1, that's just 9. Okay, so 2 1/4 is the same as 9/4. You can write it in the mixed number form, you can write it in the fraction form, whatever you need. All right, before we take off today, I got one last thing, and it's a really super important application of fractions. Ratios. Here's a problem. The ratio of the number of boys to number of girls in a summer camp is 4 to 7. Summer camp. If there are 28 boys in the camp, how many girls are there? Well, ratio is just another name for a fraction. So saying that the number of boys to the number of girls is 4 to 7 just means that that fraction would end up being 4/7. Now, we don't have 4 boys, we don't have 7 girls, evidently. It just means that for every 4 boys, there are 7 girls. And in fact, they tell us that really, the real number of boys is 28. Well, look at this. 4/7 is really equal to some other looking fraction, different looking fraction with a 28 in the numerator. Man, this sounds a lot like one of those equivalent fraction questions from our previous lesson, doesn't it? Well, how do we convert from 4/7 into an equivalent fraction with a numerator of 28? We multiply by, good, 1. 1. So what form of 1 is it? Come on, everybody yell it out. No, I 7? Wait a minute, 7 is not 1. Good fix up. Good fix up. 7 sevens. Where does that 7 come from? Where did that 7 idea come from? Excellent thinking. Look at the numerators. 4 times something better give us 28, and it's got to be 7. But realizing the whole thing that we're multiplying by is 7 sevenths because it needs to be 1, right? Got to multiply by 1. Well, 4 times 7 is 28, and 7 times 7 is 49. So the real number of girls in this camp, 49. Okay, 49 girls. All right, guys, I can't tell you how great you've been doing hanging with this. We've been going through lots of background material. You've been fantastic with it. Keep plugging away, because in our next lesson, we are going to finally see all the real numbers in all their glory, and we will be ready to move on to the next step. Excellent work. Keep working hard, and I'll see you in our next lesson. Take care.